In this video we're looking at a few interesting things about nuclear reactions, interesting observations, and how they then lead on to a really big concept in physics. So remember, a nuclear reaction, nuclear implies the nucleus of an atom, and usually it's a C, not an E. The nucleus is either splitting apart or coming together in some sort of a reaction, but the nucleus is clearly changing. Okay, in a chemical reaction, which is different from a nuclear reaction, a chemical reaction, you're modifying the way that atoms interact together. So it's an interaction between electrons, whether it's binding or loosing or ions or whatever, doing their thing. Okay, sorry chemists, I don't mean to be dismissive about that. But okay, so small interruption again, but as I said, sorry chemists, I don't mean to be dismissive. I'm just trying to focus on the physics parts of it, because chemistry is also very exciting. So chemical reaction is interaction with electrons. Nuclear reaction is change in nucleus. So nucleus or energy changes to do with the nucleus, if you like. Where were we? That's what we're reminding you what nuclear reactions were. Now, when they were observing and interacting with these, maybe not interacting, observing nuclear reactions, they look at the energy of the system and they look at the mass of the system, and or more particularly the energy, because it seemed like there was energy coming from nowhere, so there was energy being added, and that violates one of the biggest conservation laws, conservation of energy. That it doesn't happen. You don't violate that law at all. And I have spoken earlier about this. They finally worked out that there were some very subtle and small, tiny changes in mass that were the cause of it. And the linking thing between all of that was a famous equation by Einstein, E equals mc squared, where the extra energy gain came from the mass. And this constant c, the speed of light. It seems strange that the speed of light has anything to do with mass and energy, but we can also see how that's linked in relativity, but that's the proportionality constant, yeah. So I'm sorry if this is a bit all over the place. I've got lots of noise in my classroom distracting me, but you can, if I miss anything, bring it up in a discussion on the forum, embed the video there, and we can talk about it. So it's just the busy life of a teacher. So now, with E equals mc squared, we have another conservation law. We conserve in nuclear reactions the mass number, the atomic number, momentum, and now we've got this idea of mass and energy being the same thing, a mass-energy conservation. So these are all our conservation. Okay, so that's really important. So you can get energy out of an atom in the form of photons of light or electromagnetic radiation, not necessarily visible light, or kinetic energy, which is heat, so vibration of atoms, and that energy was more than they expected in any case. So now, one other place that a concept, just introducing you to it, is this idea of binding energy. The binding energy is more dealing with nuclear fission and fusion, and we're going to get into it in more detail in another video because it's a big concept. When nucleons individually, protons and neutrons, all come together to form the nucleus of an atom, they lose mass. So there's a loss in mass, and that loss in mass is this energy that's used to bind it together. It's not that you're giving it energy to glue it, so it's not like a glue energy. It's a loss in energy in the same way that something, when it falls in a gravitational field, loses energy. So it's a loss of potential energy, if you like, that's trapped in the mass of the system. So to separate them, you have to add energy to separate those nucleons. And that means if you're trying to break an atom apart, you essentially need to add energy in the right way to do that. But And some atoms will have more or less energy in their nucleus. So you might have this uranium, and then when you split it and you get some neutrons off and you get thorium, those combined might have less energy overall, and less energy overall when you add them compared to the original nucleus, and that extra energy has gone off as heat and light, and you can use that to heat water, create steam, spin a turbine, and then you've got your nuclear power station through the uranium reaction. So that's pretty cool. Binding energy, very important. We're going to get into more detail and some examples about exactly how we work that out. And we'll repeat some of this because it's a slightly tricky concept, a little bit hard to conceive of, because remember, quantum physics doesn't deal with things that are common sense and easy to understand. Common sense usually deals with things moving at a speed that we can visualize and see, and of a size that we can visualize the interactions. But these are very, very, very small subatomic particles that we're dealing with, and they move very fast, lots of energy related to their size in proportion.